I actually stands for. Yes, Jack. Square root of -1. Excellent. I is an imaginary number. I is the square root of -1. I always get students saying, why do we have to have it? Why do we have to do that? Like, why did they decide that we need an I? Because the fact is the square root of negative numbers occurs. So we have to have some way of handling it. Okay. So I is for the square root of -1. So if I have the square root of -9, as soon as you see that negative number, we're thinking of it as -1 times 9. The square root of -1 is I, so we would take the I out. And then we take the square root of 9. So we'd have plus or minus 3I. Okay. I is the square root of -1. Okay. Now, I squared, we can think of that as I times I, which is the square root of -1 times the square root of -1, which equals -1. I to the third is I squared times I. I squared is -1, so that'd be -1 times I. So I to the third is -I. I to the fourth, that's I squared times I squared. And we know I squared is -1. So we get -1 times -1, which is 1. This pattern, I, -1, -I1, this will repeat itself. For instance, look at I to the fifth. I to the fifth is I to the fourth times I. We just figured out I to the fourth is 1. So I to the fifth is I. Okay. I to the sixth, well, we can write that as I to the fourth times I squared. I to the fourth is 1. I squared is -1, so we get -1. See, the pattern is repeating itself, and it's going to continue like that. Okay? So you don't even have to memorize it. You can figure out I squared, I to the third, I to the fourth, right? And then let's say that we had something like I to the 82nd. So what we're going to do is figure out how many times 4, because this pattern repeats itself every 4 exponents. So how many times does 4 go into 82? So it gives in 20 times with a remainder of 2. This is what I care about. It has a remainder of 2, so I to the 82nd is the same thing as I squared. And I squared is -1. Okay. If I wanted to know I to the, let's do 43rd, right? How many times does 4 go into 43? 10 times with a remainder of 3. So this is what I care about. So this is equal to I to the third, which is -I. Okay. Now, it turns out that your calculator can be a big help with the imaginary numbers, because your calculator does have imaginary numbers on it. So if we look down here, right above the decimal point is the I. So if I do I to the sixth, I get -1. If I do, let's see here, let's do I to the third, right? I to the third, I get -I. So your calculator can be a huge help, right? Okay, everybody okay with that so far? Okay. Now, these are imaginary numbers. A complex number consists of a real number plus an imaginary number. Okay. complex number, the standard form is A plus BI. A and B are real numbers, and of course I is our imaginary numbers. That has to be the form of the complex number. Okay. Now, before I start showing you how to work with the complex numbers, let's just take a little side trip. I wish we had time to explore this more, because this is something that's interesting to some students that are not necessarily math maniacs like me and are more artistic, right? Have you heard of fractals? A fractal. Okay, so a fractal is something that occurs both mathematically and in nature. Okay, a fractal is something that comes from what we call a recursive procedure. A recursive procedure means that when I have a function and I get an answer, I take that answer and I plug it back in to the function. So for instance, let's say that f of x was equal to x plus 2, all right? So f of 0 is going to be equal to 2. Then I would do f of 2, which is 4. And then I would do f of 4, which gives me 6. This is a recursive procedure, okay? If you're studying, or if you're taking the computer programming course, you'll encounter this when you look at what we call arrays. And it'll be in the form of something like f of xi, and then you'll keep increasing the I. Okay, those are arrays. Well, one of the most common fractals is what we call the Mandelbrot set. I forget whether it's EL or LE. The Mandelbrot set. The Mandelbrot set was created by a man named Benoit Mandelbrot. And what he basically did, he looked at the complex numbers on the graph, and he calculated the distance between the complex numbers. And depending on the values there, he plotted a point in a certain color, okay? Complex numbers are graphed very, very easily. Instead of an XY plane, we have a real number and an imaginary number plane, or axis rather, okay? So if I'm graphing 3 plus 2i, I would go over 3 on the real number axis and to 2 on the imaginary axis, and there's my point. It's kind of graphed just like the 0.32 would be on the coordinate plane, okay? So graphing complex numbers is very easy. What Mandelbrot did is he looked at the distance between the numbers, right? So this is, let's see. This is the common Mandelbrot set fractal. Okay, really, really cool looking. When you see that, now you should think right away Mandelbrot set. And Mandelbrot set comes from complex numbers. Okay, so we don't have time to do this. This is computer generated, so you really wouldn't be able to do it. But a fractal simply means that you're taking the same result and putting it back in and getting a similar result out of it again, right? That's a recursive procedure. If you were able to zoom in enough on this, which you can if you've got the right software, you'll see that every small piece of it is the same as every other piece in the actual picture, in the actual design. So if I could zoom in here, right, you would see this little piece right here with the little nubby there. It's the same as this piece right here with the little nubby, which is the same as this bigger piece, and this is the nubby, right? So it's all the same. What I love about math is that it's orderly And God is a God of order, right? Our universe is a universe of order. It's not accident. It's not haphazard. You look in our universe, right? There are so many examples of fractals in nature. This is an example of a fractal. A pine cone is an example of a fractal. Let me actually just, fractals in nature. Right? These are all examples of fractals. Ferns, broccoli, okay? Seashells, peacocks, right? These are all examples of fractals in nature. Snowflakes. Okay, these are all examples of fractals, and they're beautiful. Okay, God is a God of order, and we see that in nature all around us. Now that you know what a fractal is, or at least you have somewhat of a knowledge of what fractals are, when you walk around, you're going to see things. You're like, oh, that's a fractal. And you've already observed things like that in nature as it is. You know that some seashells, when you look at them, you're like, oh, it's so perfect. It's just like the shape of it is so perfect, and it just repeats that same shape over and over again. Ferns repeat the same shape over and over again. Pine cones repeat the same shape, right? I grew up in what's called the Pine Barrens of South Jersey, so pine cones were everywhere. But I remember just like being fascinated by pine cones, like just pulling off one layer at a time and just seeing like, oh, it's all like every layer was exactly the same. You know, it was just fascinating. So fractals, they mean, what a fractal means is that you're taking something and you're putting it back in and you're getting the same shape, the same image, right? So when I'm talking about numerically, yeah, I was getting not the same number, but do you see that it's the same image? 2, 4, 6, right? It's repeating itself, okay? One of the projects that I like to do, if we have time, but if I can get back there now, to experiment with that is to look at what we call Sierpinski's triangle. And Sierpinski's triangle is basically, you start off with an equilateral triangle, right? And then you find the midpoint of each side, and you have another equilateral triangle, right? This is a fractal. And then you find the midpoint of each side, right? So now you've got more equilateral triangles, and then you find the midpoint of each side, and you keep doing that, and you can end up with these really cool looking artwork. Yeah, you just keep doing it and keep doing it and keep doing it and keep doing it, right? So you can end up with some really cool looking artwork, and you can do different colors and all. That's called Sierpinski's triangle. That's an example of a fractal, okay? Another example of a fractal is called the Koch snowflake, K-O-C-H, Koch snowflake. And it's the same thing, only we go out instead of in, right? So, where you can see it. Again, for those of you that are artistic, this is fun to do, okay? Okay, so find the midpoint. Bless you. I'm sorry, not the midpoint. Cut it in thirds, right? And then draw an equilateral triangle going out this time. Okay, and then you just kind of erase what's in the middle. Then you do it again here, cut in thirds. Your equilateral triangle going out. And then you do it again on each side. Cut it in thirds. Make your triangle going out. And the more sides you do, the more this ends up looking like a snowflake. And you have to admit that's kind of cool, isn't it? I know some of you like it. Some of you are like, it's pure nightmare, but it's pretty cool looking. Okay, that's called Koch snowflake. Okay. So if you do enough of them, and it will end up looking something like that. You get to a point where you can no longer continue because just physical limitations. But on the computer graphics program, you could do more and more, right? That's a fractal. You're doing the same thing on each piece, even though it gets smaller and smaller. Another one, and this is my favorite, but it's definitely the hardest one to do. It's called the Jurassic Park fractal. Okay, and that's what it looks like there. This is a good image to show you, right? Jurassic Park fractal, you're actually taking pieces of paper, cardstock, and you're folding them. And each one is folded exactly the same, right? But then connected. So each, like if you look at this image here, it has the same general shape as the next image. And this has the same general shape. And you just keep connecting it and you get this, what they call Jurassic Park fractal, because it's supposed to look like a dinosaur. I don't know how that looks like a dinosaur, but that's what they're calling it. Okay. So that's a cool one, and it's a lot of fun to do, but it's a lot of work. Okay. Okay. Excuse me. So fractals. Fractals are a type of math that is associated with complex numbers. It's associated with what we call recursive procedures. Okay, so for now, let's just get back to our less exciting complex numbers. Okay, so we know a complex number is a plus bi. So something like, where's your worksheet that we had? 2 plus 3i, that's a complex number. Now, complex numbers can be added, subtracted, multiplied, and divided, right? They work the same as if it was an x. So if we have 3 minus I plus 2 plus 3i, we just add our like terms. 3 plus 2 is 5. If this was a negative x and this was a positive 3x, we would have 2x. Well, it's the same thing, except that it's an I, 2i. Okay, so adding and subtracting complex numbers is the same. When we're working with complex numbers, notice that this is an I. We should never have anything greater than I. We shouldn't have an I squared or I to the third or I to the fourth, right? We're going to use this information up here to change it back to just plain old I or 1, okay? So if we have, like number 2, 4i times I, that gives me 4i squared. But we can't have I squared. So what does I squared equal? What does I squared equal? Negative 1. So change that to a negative 1. So this becomes negative 4. Should never have anything greater than I. Okay. So example number 3 that I gave you. What do you think we have to do with that one? 5 plus 2i, 5 minus 2i. What are we going to do? How do we multiply binomials? We have to FOIL it, yeah. So we're going to FOIL this. So we get 25 minus 10i plus 10i minus 4i squared. Okay, so I FOILed it. First, outer, inner, last. So that gives me 25. Now the 10 i's cancel. So then we have minus 4. We can't have an I squared, but I squared is equal to negative 1. So we get 25 plus 4, which equals 29. So there's our answer. Okay. Everybody good so far? Okay. How about 3 plus 2i squared? Well, if you don't remember how to expand that, we can do it the long way. 3 plus 2i times 3 plus 2i. That gives us 9 plus 6i plus 6i plus 4i squared. Okay, so we're going to continue simplifying this. 9 plus 12i plus 4. Again, I cannot have the I squared, so we put a negative 1 there. So minus 1 rather. So we have 9 plus negative 4. Well, let me just write it out in between step. Okay, so we're going to get 5 plus 12i, and that's our answer. This is in standard form. Standard form looks like this. So the I should be at the end, and it is. So that is correct in standard form. Okay. Questions so far? Okay. Division is probably the only one that I think is hard, right? Or harder. We have 2 plus 3i over 4 minus 2i. Now we know that I equals the square root of a negative number, right? Or it's the square root of a number. And we cannot have a square root in the denominator. How do you think we can get rid of this square root in the denominator? If it was 4 plus the square root of 3 down there, how would I get rid of it? Say that again? Well, if I multiply by the square root of 3, I'm going to get 4 square root of 3 plus 3. So I still have a square root down there. But you're close. You're close. We multiply by the conjugate. Remember that? The conjugate. Okay, my corny way of remembering it, conjugate it out of the denominator. Conjugate, right? Conjugate. It's like Arnold Schwarzenegger math. Conjugate it out. Conjugate, right? So the conjugate is just changing this sign. Instead of 4 minus 2i, we're going to multiply by 4 plus 2i. If that was a square root, we would do the same thing, okay? And we have to do that on the top and the bottom. So we multiply by the conjugate. Multiplying by the conjugate. Okay, so let's go ahead and multiply this out. We get 8 plus 4i plus 12i plus 6i squared. Okay, you guys should be copying this down because this is the hard one. This is the one you probably did not know how to do. And when it comes time at the end of the semester to review for your exam, you need to have notes to review. Okay, on the bottom, we get 16 minus 8i. I'm sorry, plus 8i minus 8i minus 4i squared. Okay, so I multiplied by the conjugate, right? This is the conjugate right here. But we have to do that on the top and the bottom. Now let's see what simplifying we can do. So we get 8 plus 16i plus 6. Instead of I squared, what am I going to put there? Negative 1. Okay. Over 16. Okay, now the 8 i's are going to cancel, so minus 4 times negative 1. Okay, I have 8 plus 16i, bless you, minus 6 over 16 plus 4. That gives me 2 plus 16i, bless you, over 20. Everybody okay so far? Okay. Let me just move this up here. Is this in standard form? Here's my standard form. Is that in standard form? No. So what we're going to do is separate each term. So we're going to rewrite it as 2 over 20 plus 16 over 20i. And then we can reduce that. So we have 1 over 10 plus 4 over 5i. Okay. Questions on what we did? Okay, give me a fist of 5. Okay, good. Okay, let me show you how you can check your answer on your calculator. I still want you to do the work like this, okay, but you can check yourself on the calculator. So, first off, we want to make sure that we are in the complex mode. So we go to mode, and let's see here. See down here where it says real, right here? Next to it is A plus BI. We want to make sure we're in that mode, okay? Okay, so this particular problem was 2 plus 3i. So I'm going to put in parentheses, 2 plus 3i divided by 4 minus 2i. Okay. When I press enter, okay, I get something that looks like that, right? That's decimal. I can convert that to fraction. So go to math and choose the first option, to fraction. And there we are, 1 over 10 plus 4 over 5i. Get our answer in standard form. Okay, so you can double check yourself on the calculator very easily. Okay. Okay, let me let you try one by yourself. Let's do 6 minus 5i over 2 plus 3i. Let me have you do that one by yourself. Okay, what do we multiply by? 2 minus 3i. Good, that's the conjugate. Conjugate. 2 minus 3i. Okay. So we get 12 minus 18i minus 10i plus 15i squared over 4 minus 6i plus 6i minus 9i squared, which gives me 12 minus 28i plus 15 times negative 1. And down here we have 4 minus 9 times negative 1. So that's 12 minus 28i minus 15 over 4 plus 9. So let's see, 12 minus 15, that's negative 3 minus 28i over 13. Okay, putting it in correct standard form, we have negative 3 over 13 minus 28 over 13i. Okay, I checked it on my calculator, and that's the same answer that I got. Yes?
I tried checking it on my calculator, but it just says error.
Okay, do you have it in the A plus BI mode?
Yes, I did the other one, and it gave me the right answer. It's just this problem.
Did you use parentheses?
Yes.
Oh, it looks like you used the negative sign there instead of the minus sign. I think that's the problem. Okay, anyone else? Okay, so that's division. What if I asked you to solve the equation x squared plus 64 equals 0? How would we solve that equation? Factor? We could. What if it was instead of 64, let's say it was 98? Because that's not going to factor, right? Because 98 is not a perfect square, right? Okay, since the middle term is missing, I'm going to sneeze again. Okay. Ooh. I can just subtract 98 from both sides. I can do that because there's no x term. If there's an x term, you cannot do this, right? And if there's an x term, then you have to factor. Okay, and now I'm going to take the square root of both sides. So the square root of x squared equals what? X. And the square root of negative 98. So I'm going to start by taking the I out, so plus or minus the square root of 98I. Now we need to take the square root of 98. So who remembers how to do that? Factor it down. So 98 is 2 times 49. 49 is a perfect square, right? What's the square root of 49? 7. Okay, so x equals plus or minus, we're going to do 7 square root of 2I. And that's your answer. Yes. So when we're talking about complex numbers, the I should always be at the end. So if it was like 3I or 5I, okay? So the number here, the real number part is the 7 square root of 2. So the I should come afterwards. Now, I will say that sometimes we will see it written like this. The only reason that that happens is because we want to avoid any confusion that the I is under that square root. Okay? So sometimes people will write it like that because writing it like this, we don't want them to think that the I is underneath. Okay? But this is the correct way, although this is often accepted. Okay? Does that make sense? Okay. One last example before I give you a worksheet. If I had, no, you know what? I'm going to stop there. I'm forcing the issue, and we're going to run out of time.